Thank you so much. My name is Friedrich Mu and I'm from Vialytics, as you can see. And I have a question for you. Who is working with autonomous driving or on autonomous driving? At least one person? Even more? Okay, so the question everyone has to ask himself is, where should autonomous cars drive one day? Probably not on this road.
Why not?
There's a problem. The roads in Germany are getting worse and worse, and we need to fix that. And the three founders of Vialytics saw this problem and wanted to do something about it. So they developed a system which does not actually repair the road, but which enables people who want to repair the road to do it. Because there are people who drive around and actually fix damages, but they don't know where those damages are. And this system helps. So we hand out smartphones to cities. Those smartphones can be deployed in any vehicle you would like. And this is very important because we don't want to equip special vehicles or use special equipment, because we want to make it as simple as possible. Those smartphones take images while driving, and we send those images in the cloud. And we analyze those images. As you can see, we not only analyze the images, but for data security and privacy, we also anonymize them. And I'm really excited to show you this. I worked on it. This is our algorithm in action. How we took a very screen for this. As you can see, we not only detect images, but we also detect special kinds of damages. So we differentiate cracks, we differentiate patches, open joints, which are looking in the beginning very similar, but they are not. And we want to enable the people who repair the streets to really target every single damage and fix it individually if they would want to. So after we analyze all the images, we bring it in our WebGIS, so there can be an overview where the streets are heavily damaged, where they would need fixing, and we hope, if we have gathered enough data, I have to say it, we want to use predictive maintenance to actually predict where streets are going to fail and when the best time would be to fix them to save the most money. Well, how did we do this? We use deep learning. We have an unbelievable big amount of images and so many different scenes and lightning, and can be bright, can be dark, water on the streets, rain. So we have a lot of images and a high variance in the data. So we use deep learning, convolutional neural networks, to process it and to classify where those bounding boxes are. But there are still problems, obviously. Neural networks can overfit really hard, so they learn the data too much and they will not work on different data. If we train many neural networks with the same data, we can get different results, where one network is better than the other for different classes. And the optimization is also a problem. So what do we need? We need the highest possible amount of accuracy, because we want to find every single damage that is out there and really make it possible to target every single damage for repair. What have we? We have computational power because we are on the cloud, and it's not a real-time approach, so we also have a lot of time. The solution for this would be ensemble learning. Two heads are better than one also applies for machine learning algorithms in general, not only for our neural networks. And I want to show three approaches how one could improve the performance of neural networks. But you have to put in more time, obviously, because you run multiple models. The first one would be bootstrap aggregating or bagging, which is where you build many random data sets which feature the same samples or less features from your original data set. So in the end, you end up with many randomized data sets, where on each randomized data set you can train your own predictor, your own machine learning algorithm, and in the end combine all the results to one hopefully correct answer. A very, very famous example for this would be random forest, where you train multiple different decision trees and predict the sample with all the decision trees. The next one is boosting. So boosting is built kind of like a chain. It's not about building a bunch of different predictors, but to build one predictor, and on top of that predictor you build the next one. So especially considering the errors the previous predictor made. And in this way you can build a chain of predictors, each correcting the error of the previous predictor. And in the end, again, you will hopefully get the correct result. An example for this would be ADA boost or gradient boosting machine. And stacking generalization. We found this in the Kaggle challenge, where one competitor used stacking generalization, where you build many predictors, use the outputs of the predictors to train the next predictor. So it's actually like the stacking process you could compare it to a neural network, where each single neuron in a layer is an own standalone machine learning algorithm, and in the end you train on the next layer of machine learning algorithms, only considering the outputs of the previous ones. An example would be StackNet, and it is utilized by Casanova, the Kaggle Grandmaster number 5 currently. And for us, this is a very interesting approach. So we are trying now to really bring a StackNet kind of approach to object detection, because object detection is not the same exactly like classification and regression, and we want to use stacking generalization to build really a platform which could be open source, and consider also the different kinds of predicting outputs and inputs. So not only classification or bounding boxes, but also label maps. And in this way, we can also use our already trained models, because in uncountable failures, we have a lot of models which do not perform like our best model, but in this way we could also use them to improve our performance. So, thank you for listening. If you have any questions, you can ask me now or later. And if you have later any questions, you can contact me via email or, yeah.